So, so in this lecture, we will be starting the next session, session 7. So in this session, we will be discussing about mobile transport layer. In the last session, we have discussed mobile network layer. Here we will be discussing mobile transport layer. That is, so here mainly we will be focusing on TCP protocol. The existing TCP protocol that is used in wired networks cannot be used as such for mobile communications or for wireless communications. Some improvement should be done on the existing TCP protocol so that it will support mobility. So why that improvement should be done? If that improvement does not, if you are not doing that improvement, then what will happen? And what are the ways in which it can be improved? All those things we'll be discussing in this session. Okay. So these are the topics we'll be discussing. So first we'll be trying to understand how traditional TCP works in terms of congestion. When a congestion occurs, how traditional TCP handles it through slow start or fast retransmit or recovery. And then we'll be discussing several classical TCP improvement techniques in order to support mobility, like indirect TCP, snooping TCP, mobile TCP, fast retransmit and fast recovery, transmission or timeout freezing, selective retransmission, transaction oriented TCP. All these things we'll be discussing under classical TCP improvement techniques. Okay, and then we'll be discussing TCP over 2.5 and 3G wireless networks. So this is the brief overview about this particular session. After going through this session, the learners will be able to understand why traditional TCP cannot be used for wireless communication or mobile communication, because the traditional TCP follows some mechanism, or it has some assumptions regarding congestions, but that will not work with mobile networks. So they'll be able to understand various classical TCP improvement techniques like indirect TCP, snooping TCP, mobile TCP, and other techniques. And also they'll be able to understand like how TCP can be used for 2.5 or 3G wireless networks, right? So let us start with the introduction. Okay. So let us so before going to the actual working of traditional TCP, let us have some intro session, right? See, supporting mobility only on lower layers up to network layer is not enough to provide mobility support for applications. Okay, because applications will be in the top layer. So already we have discussed mobility on IP up to IP layer. So supporting mobility up to IP layer alone is not sufficient. Okay, because most of the applications they depend on transport layer protocols such as TCP and UDP. The transport layer protocols mainly performs two functions. These are checksumming and multiplexing and demultiplexing of data. Mainly, the transport layer protocols perform two functions, which are checksumming and multiplexing and demultiplexing of data. The network layer addresses the host. Okay, the network layer addresses the host, that is a particular computer, whereas ports in the UDP or TCP are addressed, whereas ports in the whereas ports in the are addressed through UDP or TCP protocols. Okay, because ports are in UDP or TCP protocols, which allow the dedicated applications to be addressed. Right. Finally, two applications only are communicating. Okay, the network layer provides addressing for the host, but to address an application, you need ports, and those ports are available with UDP or TCP protocol. UDP provides connectionless service, and also they do not provide any guarantee about reliable data delivery. Okay, so so the mobility support that is provided in IP is enough for UDP to work. The mobility support that is already provided in IP is enough for UDP to work. That is, for UDP, we do not need any additional improvement so that it will work in a mobile network. It's not required because UDP provides a connectionless service, and it provides the and it does not guarantee about reliable data delivery. But that is not the case with TCP. Okay, but that is not the case with TCP. TCP is quite complex. So TCP needs some special mechanisms, some improvements are required so that TCP will work with mobile environment or with wireless environment. Okay. The main difference between UDP and TCP is that TCP provides connection oriented service. Okay, and using the connection oriented service, TCP provides certain guarantees like in order data delivery, reliable data transmission. TCP also has a built-in mechanism to behave in a network friendly way. That is, if TCP encounters packet loss, it assumes that the network is congested. If TCP encounters packet loss, it assumes that the network is congested, and automatically it performs and automatically it slow down the transmission, and automatically it slow down the transmission. But UDP does not behave in such a way. UDP does not provide any network friendly manner. It won't behave in a network friendly manner. It won't pull back in case of congestion and continues to send packets in the already congested network. Okay, but this particular behavior of TCP is fine for wired network. Okay, this particular behavior of TCP is fine in wired network, because in wired network most of the time packet loss happens because of congestion. Okay, in wired network most of the time packet loss happens because of congestion, but that is not the case in wireless mechanism. In wireless, that is not the case in wireless communication. Okay, in wireless communication, the packet loss not always happen due to congestion. So the traditional TCP that is used in the wired network cannot be used in the wireless networks. Okay, the main problem with many mechanisms of traditional TP is that they have been designed for situations that are completely different from those in mobile networks. So based on these problems, if we use the traditional TCP in the mobile network, it will lead to a complete breakdown of TCP traffic. Okay, so a set of solutions were proposed as classical as improvement to the classical TCP. So these solutions we will be discussing in this particular session. Okay, so this is the intro about this particular topic. Okay, so here in wireless networks, if there is a packet loss, that is mainly due to transmission error. But that is not the case in wired network. In wired network, it is due to congestion. So always when there is a packet loss, the TCP will assume that is a congestion. So that behavior will not help in wireless network. That is the key takeaway point here. So, so now let us try to understand how the traditional TCP behaves. Let us try to understand how the traditional TCP behaves when there is a packet loss. Okay. Traditional TCP is actually designed for fixed networks with fixed end system. Okay, that is for wired networks, right? And data transmission takes place using network adapters, fiber optics cable, copper wires, all these special hardware. With this hardware, data transmission happens. So there is very less probability of packet loss due to transmission error. There is very less probability of packet loss due to transmission error. Most of the time, if there is a packet loss, that is due to congestion. Most of the time, if there is a packet loss, that is due to congestion. Okay, so traditional TCP, what it does in the sense, whenever there is a packet loss, whenever there is a packet loss, that will be identified by the missing acknowledgement. That will be identified by the missing acknowledgement. Okay, so whenever there is a packet loss, the receiver notifies a gap. Okay, now the receiver will not directly tell the sender that the packet is missing. No, but it continue to acknowledge all in sequence packets up to the missing one. Okay, so the sender will notice the missing acknowledgement of the lost packet and assumes there is a packet loss due to congestion. This is how traditional TCP works. That is, whenever there is a packet loss, once the sender identifies that some acknowledgement is missing, then the sender will assume that the network is congested. Okay. So retransmitting the missing packet is unwise because this may further increase the congestion. Okay, it may further increase the congestion. Okay, so now assuming that there is a congestion, to mitigate congestion, TCP slows down the transmission dramatically. TCP, transmission control, traditional TCP in wired network, what it will do in the sense, the moment it knows that there is a missing acknowledgement, it will assume it as a congestion, and it will reduce the traffic rate dramatically. Okay, and all other TCP connections experiencing the congestion will also do the same thing. So what will happen in the sense, the congestion will soon be resolved. The congestion will be soon resolved. Okay. So this cooperative mechanism of the TCP actually helps very much for the internet. So that internet is working. Otherwise, internet may not work effectively. Okay. So this is how overall TCP behaves when there is a congestion. Okay. So so TCP performs something called a slow start when there is a congestion. So what is slow start? Let us discuss here. So, so TCP's reaction to a missing acknowledgement is quite drastic. It's quite drastic. Okay. So whenever there is a missing acknowledgement, it will drastically reduce the data rate. That process is called a slow start. That process is called as slow start. So the sender, that is the sender is the one which is going to reduce the data rate. The sender will calculate something called as congestion window for the receiver. And the TCP sender will set the start size of the congestion window as one segment. That is, in one segment, it can send only one TCP packet. Now the sender will send one packet to the receiver and it will wait for the acknowledgement. If the acknowledgement is received, then it will double the congestion window. Then it will double the congestion window. Next time it will send two packet and it will wait for the acknowledgement. Now again, after receiving two acknowledgements, it will double the congestion window. It will send four TCP packets and wait for acknowledgement. If all the four acknowledgements are received, then again it will double to 8. Okay, like this it continues. Like this it continues. So this is called as exponential growth of the congestion window in the slow start mechanism. It started slowly, but it started increasing the congestion window, doubling. So that is called as exponential growth of the congestion window. That is called as the exponential growth of the congestion window due to slow start. Actually, it is too dangerous to double the congestion window because the steps might become too large. Okay, from 128 it will become 256, then 512, 1024, 248, like that it will double. So it is actually dangerous. The exponential growth, so this exponential growth, but slow start will not keep on going with exponential growth forever. Okay, there is a limit for the exponential growth. The limit for the exponential growth is called as congestion threshold. So TC, so the slow start will continue with exponential growth up to the congestion threshold until the congestion threshold is reached. Once the congestion threshold is reached, now the congestion window will be incremented by 1. Beyond the congestion threshold, beyond the congestion threshold, the congestion window will be incremented by 1. Okay. Okay. How long it will be incremented by 1 in the sense, until it receives acknowledgement for all the packets. Okay. So linear, so now it becomes linear increase. So this linear increase continues until a timeout at the sender occurs. This linear increase continues until there is a timeout at the sender. Timeout in the sense, the sender is not the sender is not sending acknowledgement for some packet. It means that there is a packet loss. Okay. In that case, again TCP, what it will do in the sense, so it can be two cases. Either the acknowledgement may be missing, or sometimes it may send duplicate acknowledgements. Duplicate acknowledgement also means that some packets are not received at the receiver end. Okay. In either case, the sender set the congestion threshold to half of the current congestion window. Okay. Whatever the current congestion window, whatever the current congestion window, uh, to that it will set the congestion threshold to half of that. If the current congestion window is 24, then it will set the threshold as congestion threshold as 12. Okay. If the current congestion window is 1024, then it will set the threshold window as 506, 512. Okay, like that it will set the threshold. This threshold will be the half of the current congestion window. Okay, so after setting the threshold to half of the congestion window, once again TCP will make the congestion window size to one segment. Congestion window size to one segment. Okay, and again it starts sending single segment. Okay, so then again it will start the slow start. The exponential growth starts once more up to the congestion threshold. Then the window grows linear fashion. Okay, so after setting it to half of the congestion window, again after setting the congestion threshold as the half of the current congestion window, once again it will set the congestion window as 1 and start the communication in slow start fashion. That is, again it will keep doubling the packets that are transmitted every time until it reaches the threshold. Okay, after it reaches the threshold, it will linearly increase. So this process continues. So this is what is called as TCP slow start algorithm. This is called as TCP slow start algorithm. Okay. So the next thing is, so all these are how traditional TCP works. Okay. Then the next is fast transmit or fast recovery. Okay. So fast transmit or fast recovery, how it works in the sense. So two things, because of two reasons, congestion threshold, because of two reasons, the congestion threshold will be reduced. One is the sender receives continuous acknowledgement for the same packet. Okay, and the other one is the missing acknowledgements. Okay, so so if so if continuous acknowledgements are received for the same packet, this informs two things. One is that the receiver is getting one is the receiver is getting all the packets up to the acknowledgement in sequence. Okay, and the other thing is that the the receiving acknowledgement from a receiver also shows that receiver continuously receives something from the sender. Okay, the gap in the packet stream is due to severe congestion. The gap in the packet stream is not due to severe congestion, right? See, if the sender is getting multiple acknowledgements, if the sender is getting multiple acknowledgement for the same packet, then it represents two things. It represents that the sender has received up to the particular packet, up to that particular packet for which he is sending the acknowledgement, and also he has received all the packets until the until that particular packet in sequence. Okay, so in this case, most probably the packet loss may not be due to congestion, but may be due to some transmission error. So the sender can now just retransmit the missing packet before the timer expires. So the sender can now just retransmit the missing packet before the timer expires. This behavior is called as fast retransmit. This is called as fast retransmit. Okay. So the receipt of the acknowledgement of this particular packet shows that there is no congestion. Okay. So this is one improvement. So instead of directly going with slow start, the sender may just to try resending the packet, and and if there is acknowledgement, then there is no need to go for slow start. Okay, the sender can continue with the current congestion window. So the sender performs a fast recovery from the packet loss. Okay, so this mechanism can improve the efficiency of the TCP dramatically. Okay. The other reason for activating slow start is a timeout due to the missing acknowledgement. Okay. See, uh, but but if there is a timeout, but if the sender is sending a packet and within the particular time, if the acknowledgement is not received, within the particular time, if the acknowledgement is not received, then the TCP may initiate the slow start. Okay. So this is about congestion control, slow start, and fast retransmit or fast recovery in traditional TCP. Next, we will try to understand the influences of mobility on TCP mechanism. See, TCP, whenever TCP assumes congestion if packets are dropped. Whenever there is a packet drop, TCP assumes that there is a congestion. So this may not be correct with wireless networks, because in wireless networks, most often packets will be dropped due to transmission error. Okay. Further, mobility can also cause packet loss. If a mobile node roams from one access point to another, while there is while he is communicating with somebody else, then also there may be packet loss. So most of the time here, packet loss does not happens due to congestion, but due to other reasons. Okay. So the performance of an unchanged TCP can degrade severely. Okay. So we cannot use the same TCP that is used in the wired network in wireless network. Okay. But still, the key is, however, TCP cannot be changed fundamentally. However, you cannot change the TCP. That doesn't mean that you totally change the TCP. However, okay, you cannot completely change the TCP just to support mobile users or wireless links. Okay. So like how we discussed in IP, you cannot completely change the IP, because already there are many users in wired network who are using this TCP. Okay. So there are many installed computers using TCP, and it is too large to be changed. And more important is, mechanisms such as slow start keep the internet operatable. Okay. Without slow start, internet will not be surviving. Okay. So every enhancement to TCP should remain compatible with the standard TCP. Standard TCP in the sense, the TCP that is used in the fixed networks. So we cannot change the TCP. On top of the existing TCP, we can add some features so that it supports mobility. On top of the existing TCP, we cannot drastically change the TCP. We can add some additional features on the existing TCP so that it supports mobility, right? So this is the crux about this introductory part, right? So we have discussed the introduction to TCP, why TCP alone should be changed, why UDP need not be changed, and how traditional TCP works, what is congestion control, what is slow start, what is fast retransmit or fast recovery, and what is the implications on mobility with respect to TCP. So these are the things we have discussed in this particular lecture. Fine, let us stop here. Thank you.